sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Power. Tower.
I have here the Saturn V rocket. Well, not the real one, of course. This is just a model, but it's pretty accurate. I mean, look, I even wrote United Status across the side. Oops. Anyway, this massive vehicle took Apollo 11 astronauts into orbit and to the moon. But how is that even possible? Well, before I answer that question, I'm going to give some preliminary information about the rocket. It stands at 111 meters tall. But what does that even look like? For scale, picture it on the high school track. But the Saturn V was definitely on the larger side as far as rockets go, clocking in at an astounding 2,965,000 kilograms. My goal with this project was not just to get this 3,000-ton, 35-story building off the ground. I wanted to explore the relationship between required fuel and rocket mass. I attended a lecture at UCLA while visiting my sister there. It was her space sciences class, and one fact that I heard really stood out. 98% of a rocket's mass must be fuel. It sounds absurd, and I simply refused to believe it at first. So, with this project, I intended to figure out whether that is actually true, but most importantly, why. What does this 98% rule mean, though? Say I wanted to get a person up into space. The average person weighs 62 kilograms, and so, according to our graph, 62 kilograms needs 3,038 kilograms of fuel just to get it up there. This is completely absurd, but it checks out. The total mass would be 3,100, and 62 makes up 2% of it, while the 98% is pure fuel. The most basic reasoning for the 98% rule comes down to this. Once you have enough fuel to carry your mass up into space, you need more fuel to carry the added mass from that fuel. This effect continues down the rocket, resulting in the majority of your fuel being used for the sole purpose of carrying other fuel up with you. Naturally, rockets want to be as fuel efficient as possible, and so they employ a process called staging. Once I use all the fuel down here, there is no need for the extra mass hanging as dead weight, and thus I can empty the first stage worth of fuel, and then drop the stage to the ocean below. This results in decreasing my mass in two different ways. One, from the aluminum canister from the stage, and two, the air inside of the stage. The inside needs to maintain the same pressure as it uses fuel, and so it pumps helium gas into the fuel canister as it burns. And so when I discard the stage, that helium gas, the weight also goes off. Now I have my new rocket burning at the second stage. Once I use that, this part comes off, and I'm on to the third stage. And it continues to the last one. This overall decreases the amount of extra weight my rocket has and betters the fuel efficiency of the entire flight. So what's actually driving this rocket forward? Well, to put it simply, there are three main forces. The force of thrust accelerating it upwards, the force of gravity pulling it down, as well as the drag pulling it down. But don't worry, it gets far more complicated. Let's break down these forces, beginning with the force of thrust. Here's the equation for it, and dmdt stands for the rate per second at which fuel in kilograms is exhausted. VE is the exhaust velocity of the burned fuel. PE is the pressure of the exhausted mass, so the pressure inside the fuel tank. P naught is the outside atmospheric pressure. And AE is the area of exhaust, so the bottom area that the engine shoots the mass out of. Next, with the gravity, it consists of the gravitational constant, G, and then ME is the mass of Earth, M is the mass of our rocket, R is the radius of Earth, and Y stands for the altitude. Last, we have drag, and here's the equation. The Greek letter rho stands for the density of the outside air, A is the cross-sectional area of the front of the rocket, CD is the drag coefficient, which is 0.4 for the Saturn V, and this basically relies on the aerodynamics of the rocket. Lastly, V is the velocity. To calculate the net force on the rocket, we'll subtract the negative forces from the positive ones. So the thrust force minus the drag minus the gravity. And here at the bottom, you can see a color-coded equation of the entire net force. But it gets more complicated than this. The force of thrust is always parallel to the rocket's direction of motion, and so is the force of drag. But the gravity does something different. When it is at an angle, when the gravity points down, only part of our gravitational force is actually counteracting our velocity, the part of it that is parallel. And so, to find this, we can use simple trigonometry. We know our angle with respect to the ground. It's our gamma, that is our angle. And so, using opposite vertical angles, this is also gamma, and since this is a complementary pair, this is 90 minus gamma, and this would be gamma. And so we can do Fg sine of gamma to find our force parallel to the direction of motion. Okay, and coming back to these equations, I'll go ahead and put that trigonometry in. And the next step is using Newton's second law of motion. Force equals mass times acceleration. We can rearrange it to solve for acceleration, and so if we divide our entire net force equation by the mass, we will get our total acceleration. And here it is laid out. The issue, however, is that this equation decided to be more difficult than it already is. There are a lot of variables in it that are constantly changing. The rate of change of mass is different between stages, and so is the velocity ejected out of the rocket, as well as the pressure outside as we climb through the air, and even the area of ejecting between the stages because they use different engines. The density of the atmosphere is also changing as we accelerate upward, and of course the velocity is changing as well. Our gamma is changing as our rocket continues to tip to the side, and so is our y, the altitude. Even the mass of the rocket is changing. But there's one variable that kind of stands out: the pressure inside the tank. I touched briefly on this earlier about helium in the tank as it falls to the ocean, but this is due to the thrust force relying so heavily on the pressure inside the tank. If this value decreased, then the thrust force would rapidly decrease as well. And so this extra helium is pumped in to maintain pressure inside of the tank at all times. And that is what I was talking about during the staging, where all that helium mass falls to along with the outer shell. To solve this monstrous equation, I created a code in Python. It takes all these changing variables and calculates my acceleration with this equation before cycling through and changing all of those variables based on it. Then it goes again, and it computes it, and it cycles through, changing all the variables, and it goes throughout the entire launch over and over again. So let's run it and see what it looks like. The run simulation shows multiple graphs of all these variables. Here is the vehicle mass with respect to time, and then the vertical kinematics, the horizontal kinematics, the pitch profile during the burn, the forces, the total mechanical energy, the altitude profile, and, most importantly, my orbital position. After countless hours of coding, I settled on this simulation that effectively uses a Riemann sum to calculate my kinematics. I add the acceleration calculated from that equation to my velocity every second, and so my velocity continues to increase as the acceleration gets added to it. I then add my velocity to the position each second because my position changes by the velocity. The simulation is a constant loop that iterates through all of these changing variables every second and does so 700 times, which is the duration of the launch. Wait a minute, what happened to the other component of our gravitational force, the perpendicular one? Well, here's our velocity vector at the beginning of the launch, but as it goes, it begins to angle, and our velocity changes direction. The force of thrust and the drag and the gravity parallel to the rocket are causing the magnitude of this vector to change, but the direction of the velocity is changed by the perpendicular gravitational force. As the rocket goes up, the gravity gently curves its path. But why turn the rocket at all? If we could just launch it sideways at a set angle and let it fall into orbit. But this is completely not fuel efficient because it is spending an enormous amount of time in the Earth's atmosphere with a giant drag force. So what if we just go straight out of the atmosphere immediately? But the problem is now we have all of this vertical velocity shooting us off into space, and we need to somehow get rid of it, but that would just take an extra burn. The best path is a mix between the two that constantly changes its angle. It spends the least amount of time in the atmosphere as possible and gets directly up to the target altitude just as the y velocity equals 0 and the x velocity equals our orbital speed. But sometimes the y velocity doesn't get to 0. In this case, it goes into what is called an elliptical orbit. It keeps accelerating up and goes far away, but then comes back. And the reason this shape occurs is simply due to mechanical energy. When it is near the Earth, it is traveling very fast, and so it has a lot of kinetic energy. But it doesn't have that much potential energy, because the further away from the Earth you are, the more potential energy you have, and it is very close to the Earth. Because if you hold something up higher, it will have more energy than when you hold it lower, closer to the Earth. Anyway, so it uses the speed and shoots off far into space. It doesn't quite fall fast enough to come around, and so it gets very far. But by the time it's here, it has used a lot of its kinetic energy to turn into potential energy, because it's now very far from the Earth. And so it's moving slower. And this slower speed makes it not go very far before falling back down to the Earth, going fast again as it falls, getting faster and faster, and the cycle repeats. I was not taking elliptical orbits into account, and this caused an annoyingly persistent issue in my simulator. As you can see on the graph on the right, the rocket would go out and it would just keep spiraling out further and further away from the Earth because it wasn't mathematically and physically correct. It did not slow down when it got further away, and so this led it to just keep spiraling outward and ultimately creating energy somehow. But wait, before I go to jail for breaking the laws of thermodynamics, let me explain. This is where my mentors came into play. I had 3 of them. My dad, who's a chemical engineer, my uncle, who's a PhD computer scientist, and my step-grandfather, who's a PhD physicist. During a family reunion trip, we spent many hours tackling this problem with the energy, and together we came up with 2 solutions. The first error has to do with the curvature of the Earth. Say my rocket is y altitude above here, and my velocity is tangential to the Earth. So once I travel for a bit of time, my new altitude is slightly higher. And this is why the rocket in the sim was continually getting further and further out. This was because I did not take into account the centripetal force. This force is an inward-facing force, always pointing to the center of the circle, so the center of the Earth, and without this force, my rocket was continually accelerating faster and faster out into space. There's a neat derivation for this force that I will show in the corner of the next frame so that you can take a look if you'd like. But the second error correction is what finally did it. In the sim, I made it so that the moment the last engines turn off, I recorded the mechanical energy of the rocket. That is, its velocity to calculate the kinetic energy and its altitude to get its gravitational potential energy. I saved those values as a variable and made a correction every second later to the other values. If I go to the next step and I have a little bit too much mechanical energy, it would subtract just enough from the velocity so that I would have the same amount of mechanical energy as I did the previous second. And what this did is resulted in an elliptical orbit. So what is the result of all of this? Well, the simulation calculated a 97.7% fuel to mass ratio, which is pretty accurate considering it's only a sim, but more importantly, it revealed why this percentage is so large. The majority of the fuel is used for the sole purpose of carrying the other fuel off the ground. This creates a sort of relationship between the amount of fuel and how much more is needed. If you have too much, the rocket will weigh too much and never get off the ground. But if you have too little, there won't be enough fuel to carry your other fuel up along with you. 2,965,000 kilograms is a lot, but you might not realize that 73% of this mass is burned in the first stage alone, which is the only stage that burns in the Earth's atmosphere. And don't forget another 5% of the total mass is also lost after the first stage is jettisoned. With this newfound understanding of the rocket's trip up into orbit, I cannot believe it was made back in 1969. Though I will never understand how we pulled off this astonishing feat of engineering back then, I I do understand now why 98% of a rocket's mass must be fuel. Pure liquid oxygen fuel.